So today I'll be talking about a problem we were trying to solve at Airbnb, which is that we wanted to iterate across platforms quickly and be able to try a lot of different things. I'll talk about why server-driven UI fit the bill for this purpose, and I'll deep dive into the Android implementation of that. Finally, I'll go into some case studies of how we're using server-driven UI in different ways across Airbnb. Airbnb started as an accommodations business. It's a place where you can book a home when you go on vacation and stay in. So when you book a home on Airbnb, you see a screen that looks something like this. It has some photos, it has some information about the host, and some things about check-in time and that sort of thing. We're adding new products all the time. In 2016, we added a product called Experiences that fundamentally changed the scope of our work. An experience is a local activity that you can book with a host who's an expert. And so when we went into the space and launched Experiences, it took Airbnb from just being about accommodations to being about your end-to-end trip. Since we've launched Experiences, we've launched a couple other products. And each time we launch another one of these products, we build another one of these reservation screens. So for instance, we have restaurants on Airbnb reservations, so you can see the screen for that looks pretty similar, but there's a few small differences. And we also launched co-working spaces last year. So you can see as we launched each of these products, we were building out a new screen for each one. And they were pretty similar, but different in a couple of different ways. After launching a couple of these things, we realized something. We were rebuilding nearly the same screen over and over again, multiplying our efforts across the code base. And because Airbnb is a mobile-forward company where we try to launch things on Android, iOS, and web, we were also multiplying our efforts across platforms. So after building a few of these screens and thinking about it and reflecting on what we had done, the engineers got together and thought, there's got to be a better way to do this. We can't just keep rebuilding the screen over and over again every time we launch something new. So we talked about what our ideal system would look like and what that would entail. First of all, we wanted something that would be easy to understand. The way that we launch these new products is that we work with a team that's launching a new vertical for a couple weeks, and they want to jump in and out of our code base really quickly, get a reservation working, and then go back to the other work that's involved in launching a new product. So we needed something where people could enter and exit our code base for reservations really easily. We all know designers like to paint outside the lines. So we wanted a system where we would have some guidance about what a reservation should look like, but in the inevitable case when we launch something that requires new UI or different components, we'd have a system where we could extend it. We wanted to be able to launch without a Play Store release. So especially when iterating across platforms, it can be pretty cumbersome to have to wait for branch cuts and for releases, which sometimes can get delayed and go out at different cycles. So we wanted something where we could launch without that burden. Minimize repetition. We were repeating the same work and the same boilerplate every time we built a new screen, so we wanted something that would be maintained with one fragment and one screen with just different configurations. Similarly, we wanted something that would be easy to maintain, so that when we fixed a bug on, say, the home screen, it would also be fixed on the Experiences reservation screen. After discussing this as a team and thinking about the different constraints across platforms, the solution that we came up with is something we call server-driven UI. Let's talk about how this screen gets rendered using server-driven UI. The core concept here is that the API dictates which components are rendered on the screen in server-driven UI. Taking a closer look at this API response, you can see that there's a different type for each of these row components in the API response. We're making use of polymorphism here, which in a kind of academic definition is the provision of a single interface to entities of different types. What that means in practice for our Android code base is we have one row base class, and that has an interface that has an ID and a type. And then we have a bunch of subclasses, like a map row, that implements that ID and type as well as some specific properties to that subtype. Like for instance, the map row has Latin long. And similarly, we have a link row where it has an ID and type, and it also has a deep link property, because this is a row that links out to a different part of the app. So this API response has a polymorphic set of rows that are passed in. They then get sent to the client, where the client will map those rows into a corresponding data model. So in this case, we've got a carousel row that's being mapped into a carousel data model, and so on. Very similarly, this works pretty much the same on our front-end web code. It has a similar mapping. So once the client parses those data models, parses the API response into data models, they're then sent to the rendering layer and parsed into actual components rendered on the screen. So here we've got a carousel row, a title row, and an action. And this is fundamentally how it works on iOS and web as well. We just have an API response with some components. They get passed to the rendering framework and parsed into data models. And then those data models are mapped to a UI component. So let's suppose we change our mind. We don't want to have a carousel row here. We want to have a map instead. All we have to do is change that API response to a map row. And now every platform that's using this system will instantly have that map row changed. So we can just enable that from the server and really easily change and update all of our clients. And very similarly, if we decided to change the ordering, we could just change the ordering in the API response. And things are changed across the board. So after building out the system, we had some benefits that we had not thought of initially. For one thing, we could build things once. A lot of these components and screens have performance improvements, logging, and accessibility. And additionally, on the native clients, we're saving the reservations on disk so that when the user comes back offline, they can still access their reservation. We could bake this into the system so that when a team working with us came to launch a new product, they don't even have to think about those things because they're baked into our system. The system easily accommodates changing minds. So if we decided to reskin these components or change the look and feel of them, we could still maintain the same mapping, just change the component itself. We also can reuse our existing UI library. So at Airbnb, we have a library called the Design Language System. And it's a set of components that work cross-platform. So a lot of the components have iOS, Android, and web equivalents. So we could make use of that library that already existed and just plug it into that mapping really easily. And finally, we knew it would be great to be able to launch things on our own time, but that really ended up being a big benefit. If we decide to make a change, we don't have to wait for branch cut. We can just make the change on the server. So it's really easy. So that's the story of how we built the reservation system. Let's take a deep dive into the Android code. The first step is the JSON blob is sent to the Android client. And then that JSON blob is turned into an array list of rows. The rows are our base class. Next, the base class is those instances of rows are parsed into their subtypes. Once those data models are parsed into their subtypes, they're sent down to the fragment, where we have a UI controller that will map them to the correct component, and then they're rendered on the screen. Let's take a look at the code for that second step. So for this project, we're using a library called Jackson that probably a lot of you are familiar with that deserializes JSON. The main important part of this data class that's parsing that response is that there's pretty much just one important part of it. It's this array list of rows. Then those rows get parsed into subtypes. So also using Jackson, we have some annotations declaring different subtypes for these different subtypes of rows. So this is the annotation declaring a new subtype. And then we have a name property, which corresponds to what the type is in the API response. And we have a value which matches to the value of the actual class we're deserializing this JSON object to. If you look at that actual link row data model class, a couple important things are here. First of all, it's implementing that base row data class. So it implements the interface we talked about. And it's got some properties here. The ID is a part of that implementation of the interface, And then the things like title and app URL are specific to this subtype. Let's take a closer look at this next step where we configure the UI models. At Airbnb, we have a library called Epoxy that's open source. I won't go into it too much because it really could merit its own talk, but essentially it's a library for building complex screens in the recycler view. It has a really nice declarative syntax, so it makes it easy to have one screen that supports a lot of different types of views, but only some of those views are actually rendered. So we're using Epoxy in this case to build out the reservations code base. What the configuration looks like is we have an Epoxy controller that's the thing that adds those views into the recycler view, and it has a big when statement that takes a data model and parses it into, checks what subtype it is, and then calls a Kotlin extension to actually build that into a view. And the code to build that into a view looks something like this. We're declaring what type of component this should be. So this is an Epoxy model component. And we pass in the ID from the data model. We pass in a title from the data model. And then we add an on-click listener, because in this case, when you tap on the row, we navigate you to an app URL. And finally, once these things are added to the Epoxy controller, they're rendered into the recycler view. So that's how we take this response and turn it into this screen. So after we built out this reservation system, we were talking to a lot of other teams at Airbnb who were also building out product. And it turns out they were having some of the same issues we were. They want to be cross-platform, but they're also trying to move really fast, and they have product that's iterating, and the constraints are changing as they build it out. So they found server-driven UI to also be useful for some different use cases. One example of that is a system called Wally that was built out by our host success team. It's user flows as a service. And what I mean by user flows here is a series of screens with form inputs that may or may not require some validation on those form inputs and between steps. You might be thinking to yourself, building out forms is simple, right? What could be so hard about that? Has anyone tried to list their place on Airbnb before? There's a lot of different forms, and there's a lot of things to get right. So to list your place on Airbnb, we want to make sure that the listing is accurate. We want to make sure that we're showing off all the cool things about that place that the host has to offer. And we also need to make sure that it's conforming to certain safety and regional standards. So there's a lot of different fields and a lot of complexities in our forms. I'll give you an example. So we have a screen in our listing flow that asks what type of place you're listing. And the first question asks exactly what type of space it is. So the options here are entire place, private room, or shared room. Let's suppose that we check off entire place here. The next question on the screen asks what type of property it is. So this could be anything from apartment, house, houseboat, loft, that kind of thing. Let's suppose that we check off bed and breakfast here. The first step actually gets defaulted back to private room, because the way we define a bed and breakfast on Airbnb is a set of rooms that are private. So that's just one of the first and simplest steps of our flow, and that already has some complicated validation in it. And this happens all over the app where we have like different kinds of user flows. So another example is sometimes users will see different steps of the flow depending on how they answer, or if they're in a different region, something like that. And we also do a lot of A/B testing. So sometimes we'll change the ordering of experiments, the ordering of steps. Previously, how we were handling this was a lot of client-side logic. And that gets hairy really tricky, especially when you're trying to have the same logic across 3 different clients. So it was understandably a little unwieldy. The way that the host success team decided to handle this was to take some of that client-side logic and send it to the server. So they built a system called Wally to accomplish that. The Wally API response has a few things. The first is that set of components. The first is a set of components. And that set of components looks pretty similar to what we see in the reservation system. There's also an ordered list of steps. And the ordered list of screens has validation logic. Now, Wally built out a pretty generalized system for parsing this validation. So each client implements the generalized way of parsing the validation, but the actual screen-specific validation steps themselves are encoded in this JSON response. Next, a Wally response includes a list of questions, which also include conditions for validation. And finally, Wally has answers, which could be pre-populated, previously answered, or empty state. Here's a really simple example where we have a screen with a title, a toggle row, and a next button that's currently disabled. The first part of the Wally response is some questions, and in this case, it's just an ID, and it's indicating that it's a Boolean type because it's a toggle row. There's a couple components on the screen. There's a component for the title, and there's a switch row component. Next, there's a set of steps, and in this case, it's basically just one step. You can see that there's component IDs, and then there's a next button. And that next button is disabled when the value of the Boolean question is false. So in this case, the toggle row is switched to false, so the next step is also false. And finally, there's a little bit of extra stuff in the API response to handle what happens when you actually submit that form, where does it get redirected to, and so on. Wally can also handle validating navigating between screens. So an example of that would be, this is a set of steps in our review flow. And we've got this one step that says, was there anything special that your host did? We only want to show this if the host gets a stellar rating of 4 stars or more. So the way that Wally works is it essentially hides and shows this step based on the state of the previous question. So if we gave a rating of like 2 stars to this host, this step would just go away. So Wally is another example of a system that a product team built out. Now, as these systems got popular, Wally, reservations, more and more teams were starting to build out their own systems for server-driven UI because they were finding a lot of value in it. Our front-end frameworks team actually counted there were over 10 different systems. And so they got together and thought, is there any way we could build out infrastructure to better support this, since there's a lot of things that people are building out that are probably pretty similar. Their North Star is to scale server-driven UI to hundreds of developers sustainably, because they have a small team of a couple people, basically one person per platform working on Lona. So they built out this system to have some shared infrastructure that would help teams, product teams who want to build out server-driven UI, have a little less work to do. And there's essentially three things that Lona offers. First, they have a unified format for views. Think of this as the contract between what the client expects and what the server is sending. It's basically a spec for the server-driven system. Lona also offers some backend tooling to enforce that format. And finally, Lona offers client frameworks to actually render those views if the teams want. Let's dive a little deeper into what each of these things entails. The first thing is the unified format for describing views. As I mentioned with reservations, we have a pretty extensive component library that is cross-platform and already has tons of developers contributing to it. So we made use of this for reservations, and Lona takes even more advantage of this by trying to expand it to components that are for more than just reservations, like a huge swath of our design language system. And a sample Lona response, according to this spec, is going to look pretty similar to the previous systems we've seen. We've got a component specified by an ID and a type. It has some parameters, which include content like title and subtitle. And then it has a generic set of actions. So in this case, if we tap on the row, it will redirect to a deep link. So the spec itself is fairly similar to the things we've seen before. And then Lona also offers backend tooling to enforce this format. The Lona spec is interesting because it's implemented with a Kotlin design-specific language, a DSL. And because the spec is written in Kotlin, it makes it very easy to build tooling off of, more so than if we were using JSON or YAML. So one of the sets of tooling that's based off of this is a validation layer that sits on top of services. At Airbnb, we're using service-oriented architecture, so we're going to have many different services that might want to use server-driven UI. So rather than embedding this validation into the service, it's just something that can easily sit on top of it and make sure that whatever is coming out of that backend service is something that the client will understand. And finally, Lona offers client frameworks to render the views. Here's what it looks like on Android. First, you get a JSON string that is just a JSON blob according to the Lona spec. And then you pass that JSON string into lonafile.make, and the function then will make models. That make models function will generate a list of epoxy models. Finally, those models which represent views are set on the controller and then added to the recycler view. So as you can see, this is basically 3 lines of code. It's really simple for the engineer consuming this platform to use it. One thing to note is that if you remember how reservations work, there were 3 steps: an API response, a mapping of that API response to the data models, and then the UI rendering. Lona actually kind of combines these last 2 steps. There's no intermediary parsing to a data model. Effectively, the epoxy model, which is the view being added to the recycler view, is the data model. So it takes away a lot of boilerplate that existed where you're parsing things into a data model, then parsing the data model into the view. So one of the cool things about Lona's spec being written in Kotlin is that it makes code gen fairly easy. So Lona is also taking advantage of code gen to scale this server-driven UI to a lot of developers. So for instance, there's a custom deserializer that's code gen for building epoxy models. And it looks something like this. JSON is passed into this generated method, and we get the params and content from that response. And then there's code to build the model, passing in the required parameters. And at the end there, you can see the subtitle is optional. So if that property is available in the JSON response, it will be added to the view, otherwise it won't. And this is a lot of code, so it's really nice that this is all code gen, because as we scale to more and more components with the system, these things will be automatically updated. And if there's changes, they also get automatically updated. Lona also makes use of code gen for continuous integration testing. So Lona has an extensive set of sample JSON responses, and they're generated from the Lona spec. So those can be stubbed into CI tests to make sure that when there's a change to the spec, that they actually will render and build in the clients. It's nice because as the system gets bigger and more people contribute to it, there's a lot of automatic testing. Another thing Lona is doing to make this a scalable model for a lot of different teams within one system is having different levels of integration. So all of the parts of Lona can be used together end to end to render a full screen. Or if you've got an existing system like Wally, parts of it could be used, such as using just the spec to underlie the Wally components, while Wally might still take care of the logic around actually like validating certain things. So it can be used with some of these existing systems that teams have already built out. And there's also different levels of integration on the client. So Lona can render a single component in a screen that is otherwise rendered by just custom logic, non-Lona things. It can render an entire screen, and it can also render an entire set of screens. And finally, one of the things that Lona was designed very intentionally for is versioning. So probably one of the toughest things about doing server-driven UI is the versioning. And I'll explain why. So here's a common scenario. You build out your initial system with an initial set of components, and then you want to expand to another use case. So you add more components, and maybe you change some of the properties of the existing component. You push the changes to a new app version, and then you turn the API changes on. Well, there's a problem here, and that's some users don't update. So because all of this is controlled by the server side, you have to make sure that you're not sending new things up to old clients that don't understand this new change that you have in the API. Essentially, a server-driven system has to accommodate an API that evolves faster than some users upgrade. Lona was kind of designed with this in mind, so there is explicit versioning with a client number, and it's also backwards compatible in that you can specify fallbacks. So if you send up some new fancy row, you can have old clients be sent up, say, a basic row. So just to recap here, some of the ways that Lona is taking these ideas and scaling them to a lot of developers. They let teams decide what level of integration makes sense for them. They make full use of our design language system. They validate things on the back end to make sure that clients are only receiving data they understand. They're eliminating the boilerplate of data models. They're making use of code gen to generate some of our builder classes and CI tests. And finally, Lona explicitly versions and has fallbacks so that we can support those old clients for a long time, and users who don't update won't have a broken experience. So that's a few of the different ways that we're using server-driven UI at Airbnb. If you're thinking you want to try this and implement a system for yourself, here's some tips. First, know how server-driven you want to go. We gave kind of a range here. You could have something that's really specific to a feature, like the reservations platform, that will be pretty simple to get off the ground. You can also go to the other end of the spectrum and do something like Lona that's a more generalizable system. There's pros and cons to both. So with something more specific, you'll get up and running pretty quickly, and versioning might be less of a problem. With something that's more general purpose like Lona, it will take longer to build out and there'll be more complexities, but you also get to cover more use cases. API design is really key with this system. It's important that client engineers work with backend engineers to figure out what makes sense before you start implementing on the clients. And it's especially important to think about platform differences early on. So one example I can give is sometimes on web we want to present something as a modal, and then on native, we might want to present it as a full screen. It's important to think about those things early on so you can design your API around those differences and make sure that you're covering them. And finally, consider how you're going to support older clients. This could be something like an explicit version number, or it could be a version number that's just based on your app version, or you might decide to not support older clients after a certain point. Just make sure you're intentional about it, because this is probably the most complex part of building out a sustainable server-driven system. So that's the story of how we're using server-driven UI at Airbnb to rapidly iterate across platforms. Thanks for listening. I'll be taking questions up here, and we also have Nathaniel from our Lona team to take questions as well.